Welcome to AR Maths Pro Learning Academy. In this video, I'm going to talk about relations and functions of Class 12 CBSE. Exercise 1.1 Explanation and Solutions of Part 2, Question 4 till 10. Question 4. Show that the relation R in R. Here R stands for real number. Defined as R equal A comma B such that A is less than or equal B is reflexive and transitive but not symmetric. Now, given relation R is defined in R where R is a real number. Real number means it could be an integer, fraction, decimals or irrational numbers. Any number which represents on the number line is a real number. Now, the relation is defined as A comma B such that A is less than or equal B. This is the given. We need to check, is it reflexive or not? For any A belongs to A, if you choose any number, then A comma A belongs to R. Because whatever the letter is there, whatever the number you choose, so for example, if you choose half, so half comma half, both belongs to the relation. And it is equal also. If A comma A is there, since A is equal A, then it is a reflexive. Come to symmetric. If A comma B belongs to R, then A is less than or equal B as per the relation. Okay. Now, if I say B is less than or equal to A, but at the first statement A is less than B, which means B cannot be the less than A. B cannot be less than A. Then B comma A does not belongs to R. Whereas symmetric relation says if AB belongs to R, then BA must be belongs to R. So here BA does not belongs to R. So it is not a symmetric relation. Now come to transitive relation. We know the transitive relation. If A comma B belongs to R and B comma C belongs to R, then AC must be belongs to R. If A comma B belongs to R and B comma C belongs to R, according to the relation, if AB belongs to R, then A must be less than or equal B. So here A must be less than or equal B. And here B must be less than or equal C. It should be like this. Check. A less than B or equal B, B less than or equal C. Now, if A is less than B and B is less than C, obviously A must be less than C. A must be less than C, which means A comma C belongs to R. If A is less than or equal C, then A comma C belongs to R. So, transitive is possible here. Question 5. Check whether the relation R in R, here R stands for real number, defined by R equal A comma B such that A is less than or equal B power 3, B cube, is reflexive, symmetric or transitive. We need to check whether they are reflexive, symmetric or transitive. Now first of all, relation R stands for real numbers, so it could be an integer, fraction, decimal or any irrational number. A number which represents on the number line. And here relation R defines on R. So the relation is A comma B such that A is less than or equal B cube. Now I'm gonna check reflexive. Reflexive, it is clearly observed that it is not reflexive. 1 comma 1 does not belongs to R. Why? Because if I say A comma A belongs to R, then A must be less than or equal to B power 3. Now if A is 1 over 3 and 1 over 3 power, since 1 over 2 is A and 1 over 2 power 3, they are not equal, as well as this term is not smaller. This is going to be 1 over 8 and this is 1 over 2. So 1 over 2 is bigger than 1 over 8. That's why A comma A does not belongs to R. So it is not a reflexive relation. Now, symmetric. If I say, let us consider 2 comma 9 belongs to R, then 2 is less than or equal b power 9 power 3. Obviously, this is true. But symmetric relation says, if AB belongs to R, then B comma A must be belongs to R. If I say 9 comma 2 belongs to R, which means 9 must be less than or equal 2 power 3. So 9 is not less than or equal to power 3, because 2 power 3 is 8 and 9 is bigger. So I cannot say it is less than. So the relation R is not symmetric. Now, transitive. We know the transitive. If AB belongs to R and BC belongs to R, then AC must be belongs to R. See, this is transitive. AB belongs to R, BC belongs to R, then AC must be belongs to R. Now, if I say AB belongs to R, which means A less than or equal B power 3, according to the relation. This is what I'm going to write. And BC belongs to R, which means B less than or equal C power 3. And AC belongs to R, which means A is less than or equal C power 3. Now we need to check this condition satisfies even if we keep any numbers. So I'm gonna keep, let us consider the values of A, B and C. You can choose any values, but all the values must satisfy these conditions, these three conditions. Now I choose A as 9, B as 3 and C as 2. Now if A is 9 and B is 3, this condition satisfies, because 9 is less than or equal to 3 power 3. 3 power 3 is nothing but 27. Yes, this satisfies. Okay, so A comma B belongs to R. Yes. Now come to the second condition. B is less than or equal to C power 3. So B is 3 less than or equal to 2 power 3. Yes, it is true, because 2 power 3 is 8. So 3 is lesser. So this condition satisfies. B comma C belongs to R. Now come to the third. A must be less than or equal C power 3. Then only it is transitive. Now here A is 9 and B is 2. So 9 is not less than or equal to 2 power 3, because 2 power 3 is nothing but 8 and 9 is bigger. So this does not satisfy with the condition. So A comma C does not belongs to R. A comma C does not belongs to R. AB belongs to R, BC belongs to R, but AC does not belongs to R. So the relation is not transitive. Question 6. Show that the relation R in the set 1, 2, 3 given by relation R equal 1, 2, 2, 1 is symmetric but neither reflexive nor transitive. Now let us say the set A as 1, 2, 3 and the relation R is defined on A on A. So R equal 1, 2 and 2, 1. Two ordered pair. Now check reflexive. We know reflexive. It is clearly observed that 1, 1 does not belongs to R, 2, 2 does not belongs to R, 3, 3 does not belongs to R. Ordered pair with identical elements must be belongs to the relation. Then only it is a reflexive. But in this relation, I don't have any relation like this. So it is not a reflexive. Now come to symmetric. We know symmetric. If A comma B belongs to R, then B comma A must be belongs to R. This is what symmetric says. Okay. Now in this relation 1, 2 is there as well as 2, 1 is there. So opposite is there. 2, 1 is there, 1, 2 is there. 1, 2 is there, 2, 1 is there. So it is, if A comma B, if 1, 2 belongs to R, then 2, 1 belongs to R. Yes, it is. So it is a symmetric relation. Now come to transitive. Transitive relation says if AB belongs to R and BC belongs to R, then AC must be belongs to R. Now in this question 1, 2 is there. In this question 1, 2 is there. Check. And then 2, 1 is there. But 1, 1 is not there. That is what I wrote it. If 1, 2 belongs to R and 2, 1 belongs to R, then it must be 1, 1 belongs to R. But here I don't have 1 comma 1 belongs to R in the relation. So the given relation is not transitive. Question 7. Show that the relation R in the set A of all the books in a library of a college given by R equal xy such that x and y have same page numbers is an equivalence relation. Equivalence relation means it is reflexive, transitive, and symmetric. Now, given that set of all books in a library, and relation R is defined on A such that x comma y such that x and y have the same number of pages in the book. The meaning of this one is if x is 10 in this book, if I have 10 pages, so y is also 10. Now come to reflexive. We know reflexive. All ordered pair with the same identical elements must be belongs to the relation. Now for any A belongs to A, not R. For any A belongs to A, then A comma A belongs to R. Okay, then A comma A belongs to R. Yes, it is R transitive since A comma A means A is 10, A is also 10. So they have the same page numbers. So R is reflexive. Now transitive, symmetric. Symmetric relation says if AB belongs to R, then BA must be belongs to R. If AB belongs to R, the meaning is these two books have the same page numbers. Then AB have same number of pages in the book. Now, if I say B comma A belongs to, if I say B and A have the same number of books, yes, because if A is 10, B is also 10. So B and A is also 10. So B comma A belongs to R. So it is a symmetric relation. Now come to transitive. A transitive relation says if AB belongs to R and BC belongs to R, then AC must be belongs to R. Now if I say A comma B belongs to R, which means number of pages in A and number of pages in B are the same. And then if I say B and C belongs to R, so number of pages in B and number of pages in C are same in the book. Now, number of pages in A is equal number of pages in B. And number of pages in B is equal number of pages in C. Which means number of pages in A, book A, is same as number of pages in book C. Because they are equal. So A comma C belongs to R. That means the given relation R is transitive. Question 8. Show that the relation R in set A 1, 2, 3, 4, 5 given by relation R equal A comma B such that modulus of A minus B is even is an equivalence relation. Here equivalence relation means we have to prove that this relation R is reflexive, symmetric, and transitive. Now, at first, given set A equal 1, 2, 3, 4, 5, and relation R is defined on A, then relation R equal A comma B such that modulus of A minus B is even. Try to understand even means multiples of 2. So instead of writing is even, can I write 2n? Modulus of A minus B is equal to n, where n is any positive integer. Now, we have to prove this relation R is reflexive. And we know the definition of reflexive. For any A belongs to A, any element of set A belongs to A, then A comma A must be belongs to R. Now, it is clearly observed that A comma A belongs to R for any integer, for any element of A belongs to A. How? Since modulus of A minus A is equal to 0 and 0 is an even number and it's a multiple of 2, then A comma A is transitive. Now, come to symmetric. Symmetric definition, we know it. If A comma B belongs to R, then B comma A must be belongs to R. So if A comma B belongs to R, that means modulus of A minus B is equal to 2n. Now if I take negative sign as common inside here, it will be B minus A, which is equal to 2n again, because modulus of positive sign or negative sign, it's the same. If A minus B is equals to 2n or B minus A is equal to 2n, which means B comma A belongs to R. That means the relation is symmetric. Now we have to show that the given relation R is transitive. What is a transitive relation? We know it. If A comma B belongs to R and B comma C belongs to R, then A minus B must be belongs to R. Now if A comma B belongs to R, which means modulus of A minus B is equal to n. Check, is equal to n. And if B comma C belongs to R, which means modulus of B minus C is equal to 2m. For some m comma n must be belongs to any positive integer. If I remove the modulus, this 2n will be positive or negative, and 2m will be positive or negative. Now on adding these two equations, like this, A minus B plus B minus C equal plus or minus 2 I took common, and n plus m, like this. And here positive 2 and negative 2 gets cancelled. So I got A minus C is equal to plus or minus 2n plus 1, n plus m. And I know sum of two integers is again an integer. Sum of two integers is again an integer, where k belongs to an integer. So A minus C, modulus of A minus C will be 2k. Modulus of A minus C is equal to k, where k belongs to some positive integer. Therefore A comma C is also belongs to R. So if AB belongs to R and BC belongs to R, then AC is also belongs to R, which means the given relation is transitive. Now the given relation is transitive, symmetric and reflexive, which means the given relation is equivalence. That is what we have to prove. Now second part of this question is show that all the elements of 1, 3, 5 are related to each other, and all the elements of 2, 4 are related to each other, but no elements of 1, 3, 5 is related to any element of 1, 2, 4. Now at first the given set A is 1, 2, 3, 4, 5. So we have to make subsets in such a way their difference is an even number as per the relation. Now if I subtract 1 minus 2, modulus of 1 minus 2 is 1, but 1 is not an even number. So that's why I cannot choose 1. So I can choose 1, 3 and 1, 5. So 1, 3, 5 is one set. So I consider as one set as x. And the other two elements 2, 4. That is modulus of 2 and 4 is an even number. So that is why I consider these two subsets of the set A. These subsets are called equivalence classes. Now there are few properties of these equivalence classes. The first property is X union Y, which means the union of these two sets must be equal to set A. And the second property, X intersection Y, must be phi. Phi means you don't have any common element. That is why it says this, no, these two elements, no elements of 1, 2, 3 is related to any element of 1, 4. This is what the second property says. Now what we have to write is this one. The modulus of the difference between any two elements are even. You can check. Okay, 1 minus 3, 1 minus 5, or 3 minus 5, and 2 minus 4. is even, and no elements of subsets 1, 3, 5 are related to any elements of the subset 2, 4. You can check, is there any relation in between these two subsets? There is no relation. That's why x intersection y is 5. Question 9. Show that each of the following relation in the set A equal x belongs to z. Z is integer and x lies between 0 to 12. Given by relation R equal a comma b such that modulus of a minus b is a multiple of 4 is an equivalence relation. So we have to show that this relation is equivalence, which means we have to prove the relation is reflexive, symmetric, and transitive. At first, the given relation on A is A, and where x belongs to z and x lies between 0 to 12. So set A equal 0 till 12. And the relation R is defined as a comma b such that modulus of a minus b is a multiple of 4. Now we have to show that this relation is reflexive. Okay, multiple of 4 means 4 times n, where n is any positive integer. At first, reflexive. For any element of set A belongs to A, then modulus of a minus a equals 0, and 0 is a multiple of 4. 0 is a multiple of 4. 4 times 0 is 0. So since modulus of a minus a equal to 0 and a comma a belongs to R, which means it is a reflexive. This is the definition of reflexive. For any a belongs to a, then a comma a belongs to R. Therefore, it is a reflexive. Now, symmetric. If a comma b belongs to R, as per the relation, modulus of a minus b is equal 4n, which means modulus of b minus a is also 4n. If I take negative sign as common, and modulus of negative sign is the same, so modulus of b minus a is equal 4n, which means b minus a is equal 4n. This means b comma a belongs to R. Since b minus a equal 4n, then b comma a belongs to R, which means it is a symmetric relation. And the symmetric relation says if a comma b belongs to R, then b comma a must be belongs to R. Therefore, it is a symmetric relation. Next one, transitive. We have to show that the given relation is transitive. If a comma b belongs to R and b comma c belongs to R, as per the relation, if a comma b belongs to R, which means modulus of a minus b equal 4n, and b comma c belongs to R, which means modulus of b minus c equal 4m, for some m comma n belongs to positive integer. Now, if I remove the modulus, a minus b is equal plus or minus 4n, and b minus c is equal plus or minus 4m. Now, on adding these two equations, a minus b plus b minus c, a minus b plus b minus c equal plus or minus 4n plus m. I took 4 as common, and here negative b, positive b gets cancelled. If it gets cancelled, a minus c equal positive plus or minus 4n plus m. Now, if it is 4n plus m, n plus m is an integer, which means sum of two integers is again an integer, which I say 4k, and k where k is equal n plus m. And then modulus of a minus c equal 4k. Modulus of a minus c is equal 4k, which means a comma c belongs to R. A comma c belongs to R. So if a comma c belongs to R, a minus b belongs to R, b minus c belongs to R, then a c is also belongs to R, which means the given relation is transitive. So if the relation is transitive, symmetric, and reflexive, this means the given relation is equivalence. Now, the second part of the question is also asked, but I wrote here. Find the set of all elements related to 1. Related to 1 means from the given set is this one, okay? So related to 1, the difference between them must be multiple of 4. Check. I cannot do it anything. If I subtract modulus of 1 minus 2 is 1, I cannot do it. Modulus of 1 minus 3, I cannot do it. Modulus of 1 minus 4 is 3. So 3 is not a multiple of 4. Same thing. Modulus of 1 minus 5 is possible, which is 4. So that is why I choose 1 and 5. We need to relate it to 1 only. He is asking related to 1 only. So 1 minus 9 is also 8, which is a multiple of 4. That is what I choose it. Check. This is the relation defined by multiple of 4. And then, for other than that one, I cannot do it. 1 minus 13 is possible, but 13 is not here. So the set is 1, 3, 1, 5, 9 related to 1. Okay. Since modulus of 1 minus 1 is 0, which is a multiple of 4, 1 minus 5 is 4, 1 minus 9 is 8. So this is the set, what we have to find. Question 9, part B. Given relation R equal A comma B such that A equal B. And the set A is given, x belongs to Z and x lies between 0 to 12. Which means set A equal 1, 0, 1, 2, 3, 4 till 12. And the given relation R equal A comma B such that A equal B. Now we have to prove this relation is an equivalence relation. So at first, reflexive. For any element of A belongs to A, then A equal A. As per the definition, since A equal A, that means A comma A belongs to R. Since A equal A, that means A comma A belongs to R. If A comma A belongs to R, which means it is a reflexive. No, symmetric. If A comma B belongs to R, that means according to the relation A equal B. If A is equal B, which means B is equal A. If B is equal A, that means B comma A belongs to R. This is what symmetric relation says. If AB belongs to R, then BA must be belongs to R, which means it is a symmetric relation. Now, transitive. We know the transitive relation. If AB belongs to R and BC belongs to R, then we have to prove that AC belongs to R. That is the transitive condition. Now, if AB belongs to R, which means A equal B. A equal B. And BC belongs to R, which means B equal C. Now, if A equal B and B equal C, which means A is equal C. If A is equal C, which means A comma C belongs to R. Since A is equal C, that means A comma C belongs to R. This is what relation says. Now, we prove that AB belongs to R, BC belongs to R, then we have to prove AC belongs to R, which means the given relation is transitive. If the relation is reflexive, symmetric, and transitive, then the relation is equivalence. That is what we have to prove. Now, the relation is equivalence. Now, still the one part of the question is left. This is what the part says. Find the set of all elements that is related to 1. Related to 1 means, try to understand, this is my given set. Okay. Related to 1 means A equal A. So there is only one set which is related to A, 1, because 1 equal 1. I cannot, if this 1 equal any other element is not equal. So that is why the subset is related to 1 is 1 only. Question 10. Give an example of a relation which is symmetric but not reflexive and transitive. So at first, choose any set A as 1, 2, 3 and relation R is defined on A. I define a relation 1, 1, 1, 2, 2, 3, 3, 2, 1 comma 1. Is this a relation symmetric? We have to prove this is a symmetric relation, but not reflexive, not transitive. Symmetric relation says if AB belongs to R, that means BA must be belongs to R. So if 1, 2 belongs to R, 2, 1 must be there. Yes, it is there. So these two ordered pair satisfies symmetric condition. And if 2, 3 belongs to R, which means 3, 2 belongs to R, which means these two relations, these two ordered pair also satisfies symmetric condition. This is what I wrote. At first, 1 comma 2 belongs to R, then 2 comma 1 belongs to R. And at second, if 2, 3 belongs to R, 3, 2 belongs to R, which means the given relation is symmetric. Now, I'm gonna check for reflexive. A reflexive relation says for any element A comma A must be belongs to R. I don't have any element, any ordered pair which has identical elements, which has the same elements. I don't have anything. So one example is more than enough. Since 1 comma 1 does not belongs to R, 2 comma 2 does not belongs to R, 3 comma 3 does not belongs to R. So the given relation is not reflexive. Third part, transitive. Transitive, the definition of the transitive says if AB belongs to R and BC belongs to R, then AC must belongs to R. Now, for example, let us have one ordered pair. If 2, 3 belongs to R, 2, 3 is there, check. And 3, 2 belongs to R, yes. Then 2, 2 must be belongs to R, 2, 2 must be belongs to R. But in this one, I don't have 2, 2 belongs to R. In this relation, I don't have 2, 2 belongs to R, which means the given relation is not transitive. Section 10, part 2. We have to consider a relation which is transitive, but neither reflexive nor symmetric. I choose a set A as 1, 2, 3 and a relation R on set A. R equal 1 comma 2. Just one ordered pair. Let us check first, is it reflexive or not? As we know that 1 comma 1 does not belongs to R, which means this is not reflexive. The reflexive definition says if any element belongs to A, then the same ordered pair with the same element must be belongs to R. I don't have that one. 1 comma 1 does not belong to R, 2 comma 2 does not belong to R, which means the given relation is not reflexive. Check symmetric. If 1 comma 2 belongs to R, then 2 comma 1 must be belongs to R. But here 1 comma 2 is there, but 2 comma 1 is not there. 2 comma 1 does not belongs to R. And the definition of the symmetric is this one. If AB belongs to R, then B comma A must be belongs to R. So the given relation is not symmetric. Let us check transitive. Let if 1 comma 2 belongs to R, if 1 comma 2 belongs to R, but 2 comma 1 is not there, or 2 comma some other element is not there, okay, then I don't need to check 1 comma 1 is there. I just give an example, 2 comma 1 does not belongs to R, so I don't need to check 1 1. This is what I said. If AB belongs to R, then BC belongs to R, then AC must be belongs to R. This is the normal definition of the transitive. If AB is there but BC is not there, if BC does not belongs to R, then I don't need to check AC. I don't need to check AC. So no need to check 1 1. This is an example. I just gave an example. So it is a transitive relation. Part 3 of question 10. Reflexive, symmetric, but not transitive. So we have to define a relation which is reflexive and symmetric, but not transitive. So I choose a set A as 1, 2, 3 and relation R on A. And the relation is 1, 1, 2, 2, 3, 3, 1, 2, 2, 1, 2, 3, 3, 2. This relation I have to prove it's reflexive and symmetric, but not transitive. Now at first, reflexive. If you find all the ordered pair with identical elements in the relation, then it is a reflexive. So all ordered pair are here. And other ordered pair are optional in reflexive. So the given relation is reflexive. Symmetric. Symmetric relation says if 1, 2 is there, 2, 1 must be there. If 1, 2 is there, 2, 1 must be there. And 2, 3 is here and 3, 2 is also here. This is what reflexive relation says. Part 3 of question 10. We have to define a relation which is reflexive and symmetric but not transitive. So I define a set A as 1, 2, 3 and relation R on set A is this one, this relation. Now I have to show that this relation is reflexive. And we know reflexive, all ordered pair with identical elements are reflexive. Check, I have 1, 1, 2, 2 and 3, 3. This is mandatory. If this 3 ordered pair is there in the relation, then it is a reflexive relation. Now, symmetric. If 1, 2 is there, then it must be 2, 1 must be there. This is the definition of the reflexive. If AB is there, then BA must be belongs to R. Check, if 1, 2 is there, 2, 1 must be there. And 2, 3 is there, so 3, 2 is also there. So which means the given relation is symmetric. Now, transitive. I don't need to check all these ordered pair with identical elements. All these ordered pair satisfies reflexive, symmetric and transitive conditions. I need to check this one. 1, 2 is there and 2, 1 is there and 1, 1 is also there. It is there. So this one satisfies transitive condition. 2, 1 is there, 1, 2 is there, 2, 1 is there and 1, 2 is there, 2, 1 is there, 1, 2 is there and 1, 1 must be there. Yes, 1, 1 is there. And 2, 3 is there, 3, 2 is there and 1, 2, 2 is also there. So these two also satisfied. But if 1, 2 is there, 1, 2 is there and 2, 3 is there, 1, 3 is not there. Check, this is what I wrote it. 1, 3 is not there. If one ordered pair did not satisfy the transitive condition, then it is not a transitive condition. Transitive condition says if AB belongs to R and BC belongs to R, then AC must be belongs to R. So this relation is not transitive. 4 of question 10. We have to define a relation which is reflexive and transitive, but not symmetric. I choose a set A as 1, 2, 3 and relation R defined on A as this. This is the relation. Now we need to check this relation is reflexive or not and transitive, and then it should not be symmetric. Start with reflexive. If check all ordered pair with identical elements is in the relation, then it is a reflexive relation. For any A belongs to A, A belongs to R. So the given relation is reflexive. This part is obligatory, guys. The rest part is optional for reflexive. Now check symmetric. Symmetric, the definition of the symmetric says if AB is there, BA must be there. Like 2, 3 is here. 2, 3 is here. But 3, 2 is not there. One example is more than enough. 2, 3 is there, 3, 2 is not there. So it's not asymmetric. Another example, 1, 3 is there, 3, 1 is not there. So it is not a symmetric relation. Transitive. Transitive, we have to check one by one. 1, 2 is there and 2, 3 is there. 1, 3 is also there. Check. Therefore it is transitive. You need to check all these one like this. 2, 1 is there, 1, 2 is there, 2, 2 is also there. 1, 3 is there, 3, 3 is there, which means 1, 3 must be there, is here. You have to check all the ordered pair. Part 5 of question 10. We have to define a relation which is symmetric and transitive but not reflexive. So I choose a set A as 1, 2, 3 and a relation R defined on A such that R equal 1, 1, 2, 2, 1, 2, 2, 1. We have to show this relation is symmetry and transitive but not reflexive. Let us start with reflexive. A reflexive relation says all ordered pair with identical elements must be there in the relation. So 1, 1 is there, 2, 2 is there, but 3, 3 is not there. So the given relation is not reflexive. Come to symmetric. The definition of the symmetric says if AB belongs to R, then BA must be belongs to R. And all ordered pair with identical elements satisfies the symmetric condition. So I don't need to check these two ordered pair. So check with this one. 1, 2 is there and 2, 1 is there. That's all. So these two ordered pair satisfies the symmetric condition. So the given relation is symmetric. Come to transitive. Transitive condition says if AB belongs to R, BC belongs to R, then AC must be belongs to R. So this condition you have to check all the ordered pair. All the ordered pair with identical elements I don't need to check. By default these two ordered pair satisfies the transitive condition. Now I need to check this one. 1, 2 is there, 2, 1 is there, 1, 1 must be there. Yes, it is there. 1, 2 is there and 2, 2 is there and 1, 2 must be there. Yes, it is there. So it is a transitive relation.